Hi guys. So this is a recorded review for the midterm 2 practice. I'm going to start with things you should remember or just generally know well. The reason is, the test is going to be open book, open notes, open internet, open everything. But if you don't have some of these concepts burned into your brain, it's hard, if you're just going to start, like looking at everything, at all the possible pages and stuff, you're not going to get very far in a 2-hour exam. So these are the things I suggest you know well and very well and remember it. You can always look it up, the details, but the basics you should know. Okay, so this is a bipolar transistor with the collector, emitter, and base. Okay, we always want to operate this in the forward active region of operation, which means the base emitter junction is forward biased. That means the VBE, which means the voltage between base and emitter, is roughly higher than 700 millivolts. The higher that VBE is, the higher your collector current. Okay. And it could be, you're going to get some collector current at, say, 650 millivolts or 600 millivolts. But that's sort of roughly, you're not going to be at if you're at 2 volts at VBE, you're just not going to be the case. And if you're at 300 millivolts VBE, you're off. Okay. So that's, around 700 millivolts. The base collector junction should be reversed bias, which we're looking at the collector base being, we want the collector to be higher than the base by at least 0 volts. Okay. Okay. So assuming you're okay with all these things, then you're operating in the forward active region, and we have a large signal model for this. The large signal model is mathematically complex because we have exponentials in the current equations. And so what we typically do is we use this just to calculate the operating point. Okay. So here's the circuit model for a large signal. It should be okay in any signal level, but we just use this particular thing and just to get the operating points, bias points. So the base emitter junction is forward biased. So we've got a diode there on the input. Then we have a current source on the collector, which creates a collector current. The equation is for the collector current is I sub S. That's always given in the problems. So that's given. Exponential of VBE over VT. VT is known. Okay. 26 millivolts at room temperature. You can basically assume that for everything in the test. Okay. Times, I think I got this wrong here. So it should be V1 plus VCE over V sub A. Okay, so that's the equation for the collector current. This V sub A is also a given in the test. That's the early voltage. And VC is the collector emitter voltage. Okay, and then the base current is just the collector current divided by beta, which is the current gain of the device. Okay, and beta is also usually given. So it's given, I'm just going to say, in the test. And okay, so if you plot the collector current versus VBE, you get this exponential curve. So because of this guy, you got this exponential relationship of collector current with VBE. And then you have if you plot I sub C versus VCE out here, you have VCE changing this is for a constant VBE. So for a VBE1, right? For a particular VBE1, you get a curve like this. Out here, it's slightly high going because of the early voltage. And right around VBE1, when VCE turns into VBE1, is when VCB goes to 0. So after that, your collector current goes down with VCE and you're in saturation, and that's a bad spot. You don't want to be there. Okay, so here's the small signal model. As I mentioned, the large signal model has exponential in it. Once you plug that circuit model into a big complex circuit, you're going to have a heck of a time with the mathematically dealing with exponentials. So we created a small signal model, which is all linear components, and that's counting on looking at how small perturbations in input voltage get how they're affected by the transistor. Okay, and so this is on top of the operating point. Okay, so and this is a linearized model of the large signal model. We have the base, we have an input resistance R sub pi. It has a voltage V sub pi across it. The emitter, we got this transconductance G sub M times V sub pi. Okay, and we have R naught, which is the output resistance, and then that's a collector. And the small signal model, the GM, the transconductance, is the collector current divided by V sub T. Okay, again, V sub T is known. The collector current, you figured that out from the large signal operating point analysis. R sub pi, which is the input resistance, is beta, which is going to be a given, divided by the transconductance, which you calculated here. And the output resistance is V sub A, which is given, divided by I sub C, which is the collector current, again, that you calculated with the operating point. Okay, so this was the NPN model. By the way, I would just focus on NPNs. There's not going to be anything on PMPs in the midterm. And I think that's what you typically see. I think like most of the time I deal with NPNs for various reasons. So anyway, so we just looked at two amplifier structures in the class. One was the first one was the collector emitter amp. That's basically, this is the common emitter amp, okay, which means the emitter is in common with the input and the output. It has a load R sub C, okay, and you always have to worry about the output impedance of the amp, so that's the impedance looking in here, out, also the input impedance, because those interact with your source and load impedances. Okay, so the gain of this amp, the small signal gain, which is defined as V out, small signal V out over small signal Vn, is minus GM times all the resistances on the collector. So that means the R sub C, your collector resistance, which you plugged in yourself, in parallel with R sub 0, which is the small signal output resistance of the transistor, in parallel with like your load resistance, whatever you're driving. So that's your gain. And then the input resistance is R sub pi, so that's looking into the device. The reason that's important is because when your source, whatever's designing this amp, has a series resistance, which is typically the case, the input to the amp isn't Vn, it is Vn attenuated by Rn, which is in this case is R sub pi. So you basically right off the bat you get an attenuation of the voltage, and that drops your gain by that amount of the amp. Okay, and that's what I'm saying. So you want to make R sub n or R sub pi as large as possible, but you'll be constrained by other things. Okay, and the output resistance is the collector resistance in parallel with the R0, which is this guy we calculated right here. Okay, again, that's going to be in parallel with R sub L. Because it's in parallel with R sub L, whoever's lower there wins. So that's like a difficult problem. Okay, so that's the common emitter amp. It had some problems, and so we solved that with the common emitter amp with emitter degeneration. This gives us better control of the gain and higher input resistance than the common emitter amp. Okay, and so it looks like this. We basically, the difference is we put this emitter resistor in the emitter. Otherwise, it looks like the common emitter amp. But the gain now is minus the R sub C, basically, or the total resistance seen by this. But let's say we weren't driving anything. It'd be R sub C or R sub C in parallel with R sub L in parallel with R0. Okay, basically all the resistance you would see at the collector divided by 1 over G sub M plus RE. Okay, so here your gain isn't ever going to be as high as the gain for a common emitter amp, but if you can make the GM high enough, if the GM is high, this value is low, and basically your gain ends up being your collector resistance over your emitter resistance. Another nice thing about this degenerated amp is that the input resistance is R supply plus beta plus 1 times RE. Okay, so again, you have this case of R sub S going with this thing, but in this case, you not only have R pi, but like the common emitter, but you have beta plus 1 times RE, and beta plus 1 is like around 100. So you're going to have a much higher input resistance for this configuration, meaning that you'll be much, much less affected by the source resistance. Okay, so I suggest you basically look at that and remember it well. Thanks. Okay, guys, now let's start looking at the practice midterm. The first problem isn't that bad. So we're given certain device parameters. So I sub S, beta, V sub A goes to infinity, which means we can, R sub 0 will go to infinity. And so ignore early voltage for this problem. Okay. And so the first problem is it's telling us we have an NPN with a base emitter of 750 millivolts. We want to calculate the collector current and forward active. Okay, so the equation for the collector current is equal to I sub S exponential of VBE over VT. Okay, I sub S is 1 times 10 to the minus 15 exponential of 750 millivolts over 26 millivolts, and that gives us 3.4 milliamps. Okay, so that's the answer to A. B is calculate VBE such that our IC, our new IC is 100 times less. Okay, so if I take the second, so this is IC1, let's call this IC2, is IC1 divided by 100, or 3.4 milliamp divided by 100. I think that ends up being 34 microamps. Okay, and we're just gonna sort of reformat this equation here to bring VBE to the side, and so we end up with VBE is equal to VBE2 is VT natural log of IC2 over I sub S. Okay, so that's 26 millivolts times natural log of, I'm just going to keep this 3.4 milliamps divided by 100 divided by 1 times 10 to the minus 15. And so that ends up being 0.63 volts. Okay, that ends up being your second VBE2. Okay, so that's the answer to B. And then we want to plot the collector current versus VCE. Okay, so C4 IB is, it's given us an IB of 1 microamp. So IB is 1 microamp. I sub C is beta times I sub B. Okay, is equal, beta is given to us at 100. So it's 100 times 1 microamps, or 100 microamps is the collector current. Okay, and then we want to calculate the V base emitter in this case. So let's call that VBE3 is VT natural log of 100 microamps over 1 times 10 to the minus 15. And this guy, we put in the 26 millivolts. And let's see, what do we get for that? That is 100 microamps divided by 1. Natural log of times 26 milli. I get roughly 0.66 volts. Okay, so we plot, if we're plotting VCE versus I sub C, early voltage is we can ignore that, so it's going to be just a straight line until you get to VBE3. So until you get to VBE3. Okay, from VB, when collector emitter is less than VBE3, your collector base junction is going to be less than 0, and now you're violating the forward active requirement. Your base collector junction starts being forward biased, which is a bad thing. You're in saturation at that point, and basically your current starts dropping, goes to 0. Okay, so this is your saturated here at a point, starting at a point less than VBE3, which is 0.66 volts. Okay, and then your current is, your collector current is 100 microamps. Okay, so that's the answer to part C. Okay, so that was a warm-up problem. Things are gonna get a little more difficult. So the second problem is a problem you're gonna, sort of, it's a warm-up problem for 3 and 4, which is amplifier designs. And so the typically situation is you want a certain gain. So you need to find the small signal parameters to meet some specifications. Okay. And to do that, to get the small signal parameters, you need to calculate a bunch of operating points. So here we need to determine I sub C, IB, and VBE, which are the operating points. Points or biases, okay? And then R sub pi and R sub 0, these are small signal values. Okay, and we're given these parameters for the transistor. Okay. So let's start. Okay, let's start with calculating. So what do we have? We have G sub M is, G sub M is I sub C over VT. So I sub C, which is the first thing we need to get, is G sub m is given 10 millisiemens times 26 millivolts. Okay, so let me, where is my calculator? Come on out, the calculator. So I got 10 millisiemens times 26 millivolts. That is 260 microamps. Okay, so that's I sub C. So we got that. I sub B is just I sub C over beta. So it's 260 microamps. Beta is given at 100. So this is 2.6 microamps. Okay, so we got that. And then VBE is V sub T natural log of IC over IS. Okay, so that's 26 millivolts times, times natural log of 260 microamps divided by 1 times 10 to the minus 15 amps. So let's see what that ends up being. It's 0.683 volts. Okay, so that's our VBE. So now we got all our biases. And then, so here, notice I ignored here in this equation, I ignored the early voltage, although it was a given. But I'm gonna assume, we're not given the supply voltage, so we don't really know what VCA is. I'm just gonna assume VCA is like 5 volts or less, so reasonable power supply. And for those voltages, I'm gonna assume that it's not gonna have a big effect on the base emitter voltage, okay? And we're gonna test that basically by calculating RO in just a little bit, okay? So R sub pi is beta over G sub m. Okay, so that's 100 over G sub m is 10 millisiemens. Again, it's given. And so that is 100 divided by 10 millisiemens. That is 10K ohm. Okay, that's the input resistance. And RO, R sub pi, sorry. RO is, what is RO? I have to remember, VA over I sub C. So it's 100 volts divided by 260 microamps. Okay. That is 384 K ohm, okay, of resistance. Okay, so now sort of looking back at why I ignored the early voltage for VBE for low voltages. So let's just look at I sub C. Okay, so I sub C is I sub S exponential of VBE over VT times 1 plus VCE over V sub A. Okay, so I said V sub CE is less than 5 volts, so let's just take it as 5 volts over V sub A, so this value is like a 5% change in, so it's 5% or less change in collector current, which is not really going to affect our results very much. For the collector current, isn't, it's going to be different by 5%, etc. Base current, VBE is going to be again sort of a small change. So we're not going to be like worried about that. So I'm going to just drop that for the sake of simplicity. Okay. So now we're getting a little bit more difficult still. So now we're given a common emitter amp. So that's the first thing you have to do, is to recognize this as being common emitter. Notice that the emitter goes to ground, and what happened? Sorry, guys. So this is common emitter. The resistor goes to what? Acting funny. Sorry, guys. Let's get myself situated here. Okay, so this is a common emitter amp. Okay, because the emitter is in common with the input and the output. Note, both the input and the output, so input and output, are referred to the emitter. So that makes this a common emitter, and there's nothing else hanging off on the emitter, okay? And now it's saying that, what does it want us to do? It wants us to calculate the gain. Okay, so since we know it's a common emitter amp, we know the gain is minus GM R sub C, or minus GM, in this case, R sub C, well, times, yeah. So because the early voltage is 0, we only have to worry about R sub 1 as being the resistance on the collector. So it's minus G sub M R sub 1. Okay, and we want to figure that out when the output voltage is biased at VCC over 2, with VCC is 5 volts. Okay, so that means that we know the current through R sub 1. So the current through R sub 1 is 5 volts, which is our VCC. This is 2.5 volts minus 2.5 volts over, we know R sub 1, and that's 1 k ohm. Okay, so that is 2.5 milliamp. So that this is also, because we don't have anywhere else for that current to go, this also becomes our I sub C for Q1. Okay, so from this, we can calculate the gain. Sorry, we've got to calculate the transconductance, which we need for the gain here. GM is equal to I sub C1 over R1. It's, sorry, what am I doing? I sub C1 over VT, which is 2.5 milliamps over 26 millivolts, and that is equal to 96 millisiemens. Okay, so then the gain, I'm going to call this AV1 because we have to calculate a second gain with the second R1. So later, AV1 is minus this 96 millisiemens times R1, which is 1 k ohm. Okay, and that's minus 96x. Okay, so that's our gain for part A. Okay, for part B, we're changing R1 to 10 k ohm with everything else still being the same. Okay, so in that case, R1 in the second case is gonna be 5 volts minus 2.5 volts. That didn't change, but instead of 1 kilo ohm, now we got 10 kilo ohm, which drops our collector current, or our current through there, by a factor of 10. So it drops us down to 250 microamps. And because of that, GM is also down by a factor of 10 because the collector current's down by a factor of 10. So the GM goes to 9.6 millisiemens. Okay. And now we calculate the gain again, AV2 minus GM2. Sorry. Let me just jump straight into it. Come on. Then it is 9.6 minus 9.6 millisiemens times, now resistance is 10k ohm. And that also gives us to minus 96x. And that's not surprising because, because we kept this voltage the same and we increased R sub 1 by a factor of 10, we reduced the current by a factor of 10. So therefore the transconductance got reduced by a factor of 10. So it was a wash basically when you multiply the transconductance by the resistance. Okay, so that was that. And now we get to the big problem in the test. Okay, so this is kind of like what you would normally get at work or when you're designing something. Okay, so you are given, you got certain transistors in the lab or something, or you went and bought them with certain specifications, and you have some external, this circuit is supposed to do something. It's supposed to interface with a microphone, our favorite input interface. And that microphone has a certain input resistance, which is 10k ohm. And it's going to drive a headset, and that's got a certain input resistance, which is 2k ohm. Okay, and then we're supposed to get the gain of this guy, AV total, to be at least 10x. Okay, that's all we're given. So basically now we've got some restrictions, but then we have a bunch of freedoms. Okay, so the restrictions are we have to make sure that our input resistance of whatever we design is large enough that we don't get a giant attenuation along with R1. Because remember, R1 is in parallel with the Rin, and the lower Rin is, the bigger the attenuation and lower our gain is going to be. Okay. The same thing with R2. Remember that R2 is in parallel with our load resistance, which usually sort of defines, or is one of the things that defines the gain. And we want to make sure this value of R2 does not screw up our gain. Okay, so those are the limitations. And then we know we need a gain of 10. But we're also given a bunch of freedom, which is that they haven't limited us to any kind of power consumption. And they haven't limited us to any kind of transistor count or component count or anything like that. Okay, so when I try to solve something like this right off the bat, we're time limited here in a midterm, or maybe you're in the lab and you need to come up with something quick. You just sort of start making some assumptions and doing the design, and then sort of maybe look back on things, make sure everything's okay. So given that we do not have limitations on, let's say we're given this high source resistance, I know we want something with high input resistance, and the high input resistance amp configuration, we only know 2 amp configuration at this point. For the common emitter amp, for the common emitter amp, the input resistance is just R pi, okay? And for the degenerated common emitter amp, it's going to be r sub pi, this is Rn, is equal to r sub pi. So that part is the same as the common emitter plus beta plus 1 times r sub e. Now this beta plus 1 is already like 101. Notice beta is 100. Times r sub e, which, might be, let's say r sub e for the sake of discussion is on the same order as the r sub pi. So the input resistance of a degenerated common emitter amp is much higher than a common emitter amp. So that's probably a pretty good promising thing that we could use. So I'd rather use on my input, I'd rather use a common emitter amp with degeneration. Okay, so I'm going to call that R1. So that's the thinking there. And it's being driven by our source resistance, and then V1, small signal V1, and then VB, okay, which we still have to figure out. Okay, so that was the first problem, and that I chose a common emitter amp with degeneration to get a high input resistance, so it doesn't screw up my gain. Okay, so let's say I want a gain of at least 10 out of this. Okay, that means, let's say I make this I don't know, 15k ohm, and make this 1k ohm. That would give me a gain of 15x, which is bigger than, well, depends on the G sub m. Remember, the gain of this guy is AV1, so let's call this AV1, is R sub C, or the total resistance on the collector. Okay, so it'd be R sub C in parallel with whatever is driving. So I'm going to call that, like, let's say if I was going to drive this directly, drive R2 directly, it'd be RC in parallel with R2 over 1 over GM1 plus RE1. Okay, so now immediately hooking this guy up to a 2 kilo ohm, now we're going to have RC1 in parallel with a 2 kilo ohm, which means my resistance is going to be closer to 2 kilo ohm than it is to 15k ohm. And if it's close to 2 kilo ohm, my gain just dropped to 2 or 3x instead of 15x. So all of a sudden I got a problem. Okay, so the problem is I want high gain, but I got this low resistance that I need to drive. So given that I want a quick solution and I can throw power away and I'm not limited to any kind of limitation on the number of devices, and there's multiple solutions for this, but this is my approach generally. I like it. I'm going to use so I'm going to cascade. We talked about cascading, so we have one gain stage followed by another gain stage, okay, which I'm also going to make a degenerated, so I'm going to call that RE2, Q2, and RC2. Okay, the reason I use a degenerated common emitter amp here is because I don't want to load. I want this input resistance to be high, because the whole point was to not load down RC1 with another resistor in parallel with it to drive the gain down. So we want a high input resistance. Okay, and then I'm going to pick. And then so this guy is driving this guy, the R2, okay? And let's say I pick RC2 of 2k ohm, say. And R2 is given as take 2k ohm for us, and I'm going to make RE2, say 1k ohm. So these two guys in parallel are 1 kilo ohm. This is 1 kilo ohm. Again, my gain equation is this guy, so I'm going to just rewrite it here. So AV2 is RC2. So I'm just gonna, let me just actually put numbers in here. 2K ohm, which is a number I picked. So I'm not picking a very high gain now. And for the second stage, in parallel with 1 over G sub M, 2 plus RE2, which is 1K ohm. So this is 1K ohm, this is 1K ohm. So if I can get 1 over GM2 to be, if I can get GM2 to be high enough and 1 over GM2 to be low enough, the second stage is going to get me a gain of close to 1. Not quite 1, maybe a little bit less, but a gain of close to 1. But that's okay, because what it's doing is it's buffering this first gain stage. It's buffering this dude from this low output resistance. It's really hard to get a high gain when you have a low output resistance here. So, I already tried it. I went down the path of using a common emitter amp, and I just realized immediately that wasn't going to work. So I just want to make this a high input impedance because I want to preserve this gain here. So this guy's giving me the gain. Okay, so I'm hoping around 515x here. And then this guy, I'm hoping for, 1x or something. I just don't want it to screw up my 15x. So overall, I'll get a gain of 15 or something like that, or at least higher than 10. Okay, and again, I'm hoping my input resistance is high enough that this source resistance isn't going to screw up that gain either. Okay, so now let's go ahead and, a couple more things. So I picked 15K ohm here, I picked 1K ohm here, I picked 2K ohm. This 15 over 1 was to give me a high input resistance because I wanted this 1K ohm. This 1K ohm, this gives me, because multiplying by beta gives me a super high input resistance, so it won't get a lot of attenuation. If I had picked a lower RE1, I would have had a lower input resistance and more attenuation. But then this forced me, because I want to start with a gain higher than 10, to go to something like 15K ohm on the output. So that's why the choice of 15K ohm and 1K ohm came from. And then again, I picked the R sub C2 for this second amp to be 2K ohm. So overall, and then this one to be 1K ohm again to have high input impedance, input resistance, not to load the gain of this guy down, the first one down. And so I didn't want a high gain, so I picked RC2, to be, if I picked it to be, let's say RC2 10K ohm, it's still going to be, because it's in parallel with a 2K ohm, it's going to be close to a 2K ohm. What else? Okay, and then let's just pick VCC is 5 volts. It's like a reasonable number. You could, again, you're not limited to buy anything on this equation, so you could pick 10 volts, 20 volts, whatever you like. I picked 5 volts, seems reasonable. So the second thing I want to do is operating points. Okay, so this operating point, so this output of this first amp, I wanted to keep this relatively low, 1.5 volts. Okay, the reason for that is that gives me some flexibility here, because the collector of the second amp needs to be higher than its base for this guy to stay in forward active mode. So I want to make this 1.5 volts. It gives me a little bit of breathing room, and I can make this 2 volts. Okay, so now let's start with all these assumptions. Let's see if these assumptions were good by actually doing the calculations. So let's start with the first amp. So the IRC1 for the first amp is 5 volts. I assumed 1.5 volts here, okay, minus 1.5 volts. And I assumed the 15 kilo ohm resistance. That gives me a 230 microamp current. Let's say all of that, so let's say my input resistance to the second amp is really high. So all of that current, all of the IRC1 goes through the collector of Q1. So then GM01 is I sub C, and I'm going to check that, make sure that is the case later, is 230 microamp over 26 millivolts, and that is equal to 9 millisiemens. Okay, so if that's the case, the gain AV1 is R sub C. So it's R sub C1, and again, I'm assuming the input resistance of the second stage is very high. So it's just the gain is going to be RC1, which is 15 kilo ohms. It's going to give me minus 15 k ohms over 1 over GM1 plus RE1. So this is 1 over 9 millisiemens plus 1 k ohm. So this gives me a gain of, let's calculate it out. It's around minus 13.5x. Okay, so that's good. The gain of our first stage is above 10. Okay, but now we've made some assumptions, but we're going to come back and double check it. But at least we're starting with a gain higher than 10. It's only going to be downhill from here. Everything else is going to reduce our gain. Okay, so the next step is let's check on the gain of AV2, the second stage, this stage. Okay, and we use the same equation. Now here is, we've got RC2 in parallel with R2 here, and that we cannot ignore because that's a pretty low resistance, over the GM of the second stage plus RE of the second stage. Okay, so we need to figure out the GM of the second stage. I said I'm going to try to keep this at 2 volts, the output. So the current I sub C of 2 is 5 volts minus 2 volts divided by, I've got 2 kilo ohms in parallel with 2 kilo ohms, which is 1 kilo ohm. So that's the RC2 plus R2. Okay, so that's 3 volts over 1 k ohm. So that gives me 3 milliamps. Okay, so G sub M is IC2 over V sub T, so it's 3 milliamps divided by 26 millivolts, and that gives me 115 millisiemens. Millisiemens. And so for the gain, IV2, I end up with minus RC2 in parallel with R2 is 1 k ohm over 1 over 115 millisiemens plus 1 k ohm. So that ends up being, let me double check my numbers. So if we got 115 millisiemens, that's like 8.7 ohms. So 1 k ohm over 8.7 ohms plus 1 k ohm. So that's like minus 0.991. Okay, great. So the gain of the second stage is a little bit less than a gain of 1, which means, but it's close to 1, which is good. So when I multiply that by the gain of the first stage, I've managed not to screw up my total gain much. So it's doing a good job as a buffer. Okay. So great, so that's working out. Now I had assumed that my input resistance into the second stage was not going to load down the first stage. So let me go back and make sure that's the case now that we have are all this stuff we need to figure out Rn. So that's equal to Rn2 is R pi 2 plus, whoops, it's not R pi squared, it's R pi 2 plus beta plus 1 R sub E. Okay, so R pi 2 is beta over GM2 plus beta plus 1 RE2, okay, which is 100 over GM2 is 115 millisiemens plus beta is 100 plus 1, R sub E2 is 1 k ohm. So this ends up being 100 divided by, so this is 869 ohms plus this is 101 kilo ohm plus 101 kilo ohm, whoops, 101 kilo ohm plus 869. So that's 100 and roughly 102 k ohm, which is much bigger than RC1, which was 15 k ohm, which means we're not really, the RC1, the total resistance on this collector of Q1 is pretty much the resistance of, basically let's calculate the gain now with just that value, right? So if we look at it now, if we recalculate the gain of AV1, sorry, we end up with 102 k ohm in parallel with 15 k ohm over 1 over G sub M1 plus 1 k ohm. Okay, so let's see. 102 and plus 15. So this ends up being, let's see, ends up being 13 k ohm, okay, divided by 1 over G sub M. I'm going to say that's going to be the same as before, 1 over 9 millisiemens, which was 9 millisiemens. Let's see what that is. 111. Okay, so that gives us 11.7. So this is minus. So this is the gain of the first stage after we went and checked that, what our input resistance of the second stage was. So that's good. We're still over, we went from 13.5 to 11.7, but we're still over 10. So the next thing we want to check, so that's the gain of these two guys driving the loads and driving each other. Okay, so the last thing we want to check is, hey, what is this thing? Does this screw anything up? And hopefully not. So to do that, we need to get the input resistance of the first stage. Okay, and again, that's r pi of 1 plus beta plus 1 r sub e. And r sub pi is beta over gm1 plus 100 plus 1 times 1 k ohm. This is 100 over gm of the first stage was 9 Siemens. Okay, plus 101 k ohm. So 100 divided by 9 milli, that's 11 kilo ohm. So this is 11 kilo ohm plus 101 kilo ohm. So let's call that, so that's 112 kilo ohm. Okay, so now we've got our input looks like a 10 k ohm going into a 112 k ohm. So here we add, let's see, we got 112 k ohm plus 10 k ohm something times okay, so that is this attenuation going into the input is 0.91. Let's call this gain of 0, of the stage 0, which is just the input driving the input of the amp. So the total gain, okay, so the goal was greater than 10, is 0.91 times 11.7 times, what was the gain of the 0.991? Hopefully we're still over 10. Oof, just barely made it. 10.64x. Okay, so that's our total gain. So we met our requirement, but just barely. Okay, but and we wanted to get a quick result out. Okay, and so the last thing we need to do, so we've got all our components. So the last thing we want to do is get the VBE, this VBE, okay, which is not the same as this VBE. So I'm going to call that VBE1, okay, is V sub t natural log of IC over IS. Okay, so it's 26 millivolts, natural log. The current on the first stage was 230 microamps. Okay, divided by 1 times 10 to the minus 15 is equal to 30 microamps by 1 e to the 15. Natural log times so I get 0.68 volts here. Okay, so that's VBE1. I need to add that to, remember, we've got R sub E 1. And so now we got this, but we need to get the resistance across that. And that, the resistance is 1 k ohm, and the collector current is 230 microamps. So I of RE1 is 230 microamps times 1 k ohm. 230 microamps times 1 k ohm is 0.23 volts. And so we need to add these two guys together to get the actual VBE. of the circuit, VBE, is 0.68 plus 0.23 plus 0.68 is equal to 0.91. Okay, so here is the sort of total, okay? So we've got VN, VBE is 0.91. Then we got a 10K ohm. And we got one bipolar transistor. We got VCC is 5 volts. We got R sub C of 15K ohm. We got R sub, I'm going to call this R sub C2, R sub C1. RE1 is 1K ohm. And that is driving our second stage, 1K ohm. And that is, we said 2K ohms here, and this guy is 5 volts, sorry. And then we're driving also this load, which is another 2K ohm. Okay, V out, and then V out. And so we met our gain goal, so the total A is 10.6x, and we calculated all the parameters. Okay, that's it, guys.